Okay, the last bit of the wave characteristics, page 16 to 18, is really a bit of a review, kind of a mathematical review. Again, watch it, take a little something from it, and depending on who you are, you're going to choose your future. So, real quickly through here, and we're not going to write it out in a lot of detail, but just as a quick review, I'm actually going to give you this as part of your questions, or something just like this as part of your questions to see how you're doing on the notes. Uh, so over here it is. Here's a wave. You got displacement, which allows you to look at the amplitude, and you have the time axis, which allows you to pick frequency or period directly off of it. All right, so let's do it real quick. Amplitude, remember, is the max away from equilibrium. So this thing says horizontal displacement from A to B is 1 meter. So we know that from here to here is 1 meter. That's going to help us. We also know on the y-axis from here down to here is -2 meters. Well, actually, that lines up with the amplitude. So the amplitude here is -2 meters. Cool. Number of cycles, count them up. Starting here, we see 1, 2. Done. So there are 2 cycles here. 2 cycles. What is the frequency? Remember your 3-word definition. Cycles per time. I prefer to write cyc, but it's a little hard to write here. So what we see here total, there are 2 cycles per the time. Well, actually, here's the time axis. We see at point C it's 2 seconds, which means over here is 4, 6. The total time here is 8 seconds. So 2 cycles per 8 seconds, which is 0.25 hertz, or 1/4 of a hertz. The period is time per cycle. So the period you can either do from your equation in your reference table, 1 over frequency, so invert the frequency. That's easy enough, which would just make it 8 over 2 or 4, but I prefer you try to pull it off the actual graph. So the total time here is 8 seconds. Total number of cycles is 2. You also could have done it just for 1. Oh, look, 1 cycle took 4 seconds. Heck, you could even done it here. You could say half cycle from A to C took 2 seconds. So I'll put that one in there. It really doesn't matter which one it is. They all come out exactly the same. 2 cycles, or 2 seconds rather, per half cycle comes out to 4 seconds per cycle. All right, the wavelength. Let me switch color here. Wavelength, or sorry, number of waves. Number of waves is the same as number of cycles. There are 2 waves, 2 wavelengths here. The wavelength itself, well, you can't do distance per cycle. You could try out here distance. Oh, I'm sorry, you can. You can because I told you something. Sorry, I don't mean to confuse you on that. I told you from A to B was 1 meter. Because of that, you can do wavelength. You can do distance per cycle. You can't normally pull it off this axis, 2, 4, 6, 8. Distance per cycle. So here it was 1 meter per, that's a quarter cycle, 1 per 0.25 cycles, which of course comes out to 4 meter wavelength. Okay, wave speed, I have it 2 ways because you can do it 2 different ways. You can do it as distance over time, distance over time. In this case, you have many options. Just coordinate your givens. If you choose this 1 meter distance, that also will go with a 1 second time. 1 over 1 is 1 meter per second. If you choose this is going to be 8 meters in 8 seconds, no matter how you slice it, 1 meter per second. If you do this with lambda, frequency times wavelength, there it is. Well, the frequency we found to be 1/4, and the wavelength we found to be 4. So 1/4 times 4 comes out to 1. If we use the units from this, it's going to be hertz meters. Okay. 2 points in phase. Well, we could say B and F. There are plenty of them. Go back to the phase thing to figure it out. They should be at matching locations. 2 points that are 90 degrees out, they should be quarter wave apart, like maybe A and B, or D and E. 180 out is opposite, like B and D. And 270 out, 3/4 wave separated, like A and D. Okay, let's do one more of these down here real quick. This one instead, I gave you a distance axis, which means we can pull wavelength directly off it. And it's the same kind of game. You get your amplitude over here. We'll go even faster this time. takes 1 second to go from A to C. So from here to here is a time of 1 second. That is not the distance axis. That's a separate piece of information which you don't always get. Amplitude here is 5 meters. You see from equilibrium to the top here, 5 meters. I'm going to leave out the units. No, I won't. 5 meters. Number of cycles, there's still 2, just like above. 2 cycles. The frequency is cycles over time. Well, since I gave you the time from A to C is 1 second, that's half cycle. So that would be 0.5 cycles over 1 second. You could also notice, of course, that means you'd have 1 cycle over 2 seconds. Frequency comes out to half hertz. The period, you can invert the frequency, but it's good to remember time per cycle. So period, 2 seconds per half cycle. Or sorry, 1 second. Let me mess up my numbers. 1 second, that's this right here, from A to C, per half cycle. It would be 2 seconds for 1 cycle. Comes out to 2 seconds per cycle. All right, the number of waves before, 2 wavelengths, 2 full wavelengths shown. The wavelength here, well, now 2, 4, 6, 8. The total distance is 8 meters. So the wavelength would be distance per cycle. In this case, it would be 8 meters per 2 cycles. 8 meters per 2 cycles. And that's based on this 2 right here. I just gave you 1 data point on the distance scale, or 1 point on the distance scale. And that will give you 4 meters per cycle. The speed, you do the same business as above. Distance over time. And this one came out also, let's see, this one is 1 second, 2, 3, 4 seconds. So 8 meters over 4 seconds. This one came out to 2 meters per second, actually. And if you do this as frequency times wavelength, so this was the D over T version. If you do this frequency times wavelength, then the frequency we got to be half hertz. The wavelength we got to be 4 meters. Half times 4 also comes out to 2 meters per second, no doubt. All right, this is the same graphic as the one above, so the phasing answers will all be the same. All right, let's keep going over here. Increase, decrease, or relationship problems, as we like to call them. Relationship. Writing in scripts a little easier. Relationship problems. So again, this is more essential for those of you who going on in some kind of science, math, etc., AP Physics, all that. It's not hard. You can do it. But you'll see that the questions on this sort of relationship problems, I'm going to keep them in one sort of assignment rather than another. Okay, if a frequency of a source is doubled in a particular medium, when you read particular medium, you better jump straight to this. This is a big, big, big deal. When you read particular medium, that means the wave speed is constant, remains the same, because we're in the particular medium. Now, knowing that, all the rest is details, so to speak. We look at this equation, and this tells us everything. So, if the frequency is doubled, so now we know what happens to the period. Well, the period equation, T equals 1 over F, which do what it says. So if the frequency is doubled, just put a 2 there. 1 over 2, the frequency becomes, or the period rather, becomes halved. What happens to the wavelength? Pull this equation. Well, if we rearrange this equation for wavelength, which is going to be the best way to do it, wavelength is V over frequency. Then what happens here? Well, speed stays the same. We know that. 1 over doubled frequency. Oh, wavelength becomes halved. Energy delivered per time. Well, if you remember what we said, when frequency goes up, the energy delivered goes up. That actually will double. And basically, if you wait a minute, you are now getting twice as many waves as compared to before, so you're going to get twice as much energy delivered. All right, let's go over here. If the period is doubled in a particular medium, you know that means the wave speed must, I don't care what any equation says, if you're in a particular medium, the wave speed of a particular wave will remain the same. loud, quiet, high frequency, low frequency. There it is. That allows us to bust out this equation and mess around with that. All right, now they're asking about frequency. Well, frequency and period relate with this equation. T equals 1 over F. They want to know what happens to the frequency, so rearrange this thing to F equals 1 over T. And of course, here the period is doubled. Sorry, it's a capital T for period. The period is doubled, so it's 1 over 2, answer halved. Done. All right, what happens to the wavelength? Well, we know the period was doubled. Period and wavelength don't have an equation that connect, but you could actually do this. V equals frequency times wavelength, and this is actually a nice substitution. Since frequency is 1 over period, here it is, you can actually rewrite this equation as 1 over period times wavelength. Nice little substitution here, which is the same thing as wavelength over period. Now, of course, you can rearrange it. So V equals, connect the two, V equals, pick this piece of the multi-equation, wavelength over period. If we rearrange it, we want to know what happens to the wavelength. Wavelength is V times T in a particular medium. And here we said put the double arrow. Speed we know stays the same. And the period doubles, so the answer will be 1 times 2, 2 doubles. Finally, the energy delivered per time. Probably the easiest way to think about that one is via frequency. Half the frequency means in a minute you get half as many waves, so you get half the energy delivered per time. Boom, done. Here's one that looks a little more like a quantitative, kind of a Regent style question. Diagram, a water wave having a speed of 0.25 meters per second. We got that covered now. That's your V. Causes a cork. This is an important line right here for those of you who need to get quantitative with this. The cork moves up and down 4 times in 8 seconds. This, though it looks like kind of a vague piece of information, this is a lot of information right here. What this is telling you, 4 times is 4 cycles. Up and down, that's a full cycle. And 8 seconds is telling you the time. Now this is incredibly useful. 2 givens immediately. In fact, the 2 givens are these, period and frequency. Because period, this is where your 3-word definition comes in. Not just 1 over F, but period is time over cycles, which in this case is time, 8 seconds, over cycles, 4 cycles. And that, of course, gives you your, you see over there on the right, 2 second or 2 seconds per cycle, period. Either way, 2 seconds or 2 seconds per cycle are both fair game. Okay, so that's where this comes from. The frequency, very good, remember this 3-word definition, is your cycles over time. Over time. And so in this case, again, go back straight back to your givens, because they may not give you both of these. They give you one of the questions. So you got to start with these givens anyway. You'd have 4 cycles. I'll just drop the units this time over 8 seconds. And that's why it gives you your 4 over 8 half hertz. Okay, let's answer the other questions here because they are good review. Oop. Sorry about that. They are good review. So, is this periodic or pulse? Because you see it's regularly repeating, it's symmetric, like wave, 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 wave. This is periodic. If it were just one of these lumps, it would be pulse. Transverse or longitudinal. We're not looking at a set of scaled axes. We're looking at the actual wave. You can see that as the motion is forward, the vibration is up and down. These two are perpendicular to each other. Flip that perpendicular symbol to get yourself the capital T. Transverse is the answer. Mechanical or field. It's water. Water has mass. Remember, mechanical wave has to go through a mass medium, a matter medium, a medium with material. So this is most certainly a mechanical wave. Finally, determine the wavelength. Wavelength, you could do distance per cycle, but we don't have a distance here. So we're going to have to rearrange our Flamda equation. Speed over frequency. And that, of course, the speed we got was 0.25. They told us in the beginning, 0.25 meters per second. I dropped the units for a minute. And the frequency we got to be 0.5. So 0.25 over 0.50 gives you 0.5 meter wavelength. You could also say 0.5 meters per cycle. That's legal too. All right, good. That's like a regular old Regents run you through. Last page, nothing for you to write. This is just a review of the big six. Basically, you can have pulse or periodic, although usually we deal with those symmetrically repeating waves. All waves transfer energy, not mass. Light is transverse, meaning if the motion is forward, then the vibration has to be either up, down, or left, right, or something like that. Sound is parallel, longitudinal, which means if the motion's forward, the vibrations have to be forward, backward. Light goes through the electromagnetic field, whereas sound can go through any mechanical or matter medium, so liquid, solid, gas, basically, plasma too. Actual medium, there it is. We tend to focus on air. However, we will talk about sound in water. We'll talk about sound in steel, things like that, just a little bit. All right. Light can pass through anything. However, sound does not travel nearly as far through, where is this? Gases and liquids. Believe it or not, sound travels pretty far in gases and liquids, but not as far as solids. Of course, depends on the situation, but earthquake waves are really a type of sound wave, and through solids they go quite far. You can pass through the entire Earth. The liquid parts of Earth, the certain waves don't travel so well. Okay, amplitude, we should know, means intensity. It's the brightness of a light wave. It's the volume of a sound wave. Remember, messing with the amplitude. Amplitude down, amplitude up. And then with sound, amplitude down, amplitude up. It's also the energy of a sound wave. If you ever stood in front of a big speaker that's pumping, you'll know it. For light, let's see here. Frequency tells you the color. You saw that on PRT2. And where is it? Where is it? There they are. And it also tells you the energy. That's that high energy blue light. Hard to sleep. Make the redshift on your phone. Frequency for sound gives you the note. And we messed around with that song. Oh, here it was. Yeah, this was... Ooh. I know, make it stop. Okay. Period and wavelength, we said don't memorize it. As long as you're within a medium. Period's always opposite frequency, or inverse frequency. Wavelength, as long as you're within a medium, will be inverse frequency. This stuff we'll get to later with interference, but when two lights are in phase, they appear brighter. When they're out of phase, they appear dimmer. When their sounds are in phase, they appear louder. And so your speakers, you try to set them up that way. Multiple speakers, where you put them matters, because if they come to you out of phase, the sound is quieter, in phase louder. Finally, the speed. Speed of light in a vacuum, PRT1. Speed of sound in air at STP. Those are both from your reference table. Where is it? Here it is. On the front, speed of light in a vacuum, speed of sound in air at STP. Those are the most common speeds we will use in our problems. And then you should realize that light is actually inhibited by or slowed by materials. So it goes the fastest in a vacuum, and then it slows down as you move along here. Let me see. Oh, this graphic is backward. Ooh, correction. The next fastest material for light is gas, then liquid, then solid is going to be the slowest for light. Sorry about that. Sound, on the other hand, so note, there was a mistake there. Sound, on the other hand, goes faster in thicker materials, fastest in solid. Okay, that's it for your little review. And now we're going to get on to wave phenomena, and I think you'll enjoy this more.